Okay, hello everyone. My talk is about mixed precision iterative refinement for the solution of large sparse linear systems. And I am Bastien Vieublé. In today's computer, we have access to a wide range of arithmetic precision. It goes from half precision to single, double, and even quad precision. And they're all using a different number of bits to encode their floating point number. Of course, the more the number of bits, the more the range can be high, and the more the unit round-off can be precise. In particular, low arithmetic precision, such as half precision, are increasingly supported by hardware. They are already present on accelerators, such as GPUs, but they are also coming on CPUs. Using them presents great benefits since it can reduce storage, data movement, and communication. Also, it presents faster computations, even faster if we consider using special hardware implemented operations, such as GPU tensor cores, and it reduces the energy consumption. However, using them to solve a problem in low precision, it will make a low accuracy solution of these problems. That is why it motivates the use of mixed precision algorithms, which will tend to make most of the computation in low precision and get back on a good accuracy of the solution by making some strategic operations in higher precision. Iterative refinement is one of this algorithm. It has been introduced first by Wilkinson in 1948 and was originally meant to correct rounding errors of a direct LU solving. In iterative refinement, we first compute the solution by means of a direct solver and then refine it in refinement steps to increase its accuracy. The refinement steps is composed of the computation of the residual, the solving of the correction equation, and the update of the solution. Thing is, in iterative refinements, every of these operations can be done at different arithmetic precision. Originally, in the Wilkinson version, everything was done at precision U, standing for the working precision, except the computing of the residual, which was done at a precision U squared, which is a higher precision. Over the different iterative refinement algorithms we will review in this presentation, there are only this set of precisions and the solver used at step 5, which will change. In 1977, Jankowski and Wozniak introduced the fixed precision iterative refinement, using the precision U, the working precision, for every operation. So working precision also for the computation of the residual. In 2006, Languedol has been reconsidering iterative refinement, not just as something to improve the accuracy of the solution, but also as an accelerator on modern architectures where single precision computation is twice as fast as double precision. So the trick is here we will do the factorization, which is of the algorithm in a low precision UF, and get back on a good accuracy of the solution by making the refinement steps in higher precision. In 2018, Carson and Iam introduced a third precision to this algorithm, UR, on the residual to improve the accuracy of the solution. They provide an error analysis of this algorithm they call LUIR3, and under a certain condition on kappa A, which is the conditioning number of the matrix, they guarantee an error accuracy of order UR kappa A plus U, where if UR is chosen enough precise, it can absorb the term kappa A, and then we can have an error accuracy of order U. However, for very low precision factorization, such as half precision, it leads to a very restrictive convergence condition. That is why they proposed another algorithm, which is called GMREV-IR3, and which used at step 5 for solving the correction equation, a preconditioned GMRES by DLU factors at precision U, except for the computation of the preconditioning and the matrix vector product, which is done at a higher precision U squared. They provide also an error analysis of this algorithm, which has a far less restrictive convergence condition on kappa A. For example, for a factorization carried in half precision, the condition on LUIR3 is 2 times tempo 3, and on GMREV-IR3, this is 2 times tempo 11, which is far better. So now if we consider using LUIR3 on sparse system, in sparse, what we call the fill-in phenomenon, which is the fact that the number of non-zeros of the original matrix is far lower than the number of non-zeros of its factors. For example, for an n times n matrix from a regular 3D geometry, the number of non-zeros of A is of order n, and the number of non-zeros of its factor is of order n for third. It gives, for the operation used in iterative refinements, the following complexities. The factorization, which is the most costly, is of order n squared. The solve is of order n forced, and the matrix vector product is of order n. Thus, it leads to really important specific features when using LUIR3 on sparse, in comparison to the dense case. The matrix vector product are much cheaper than the solve. Then we can set up UR really precise, such as quad precision. Even so, quad precision may not be hardware supported. Also, the memory space of A in UR is negligible in comparison of the LU factors in UF. Then LUIR3 is able to save memory in comparison to a direct LU solving in precision U, the working precision. But unfortunately, all these good properties are not true for GMRIR3, since the LU solves are performed at precision U square, and this is a major practical issue, because it increases the cost per iteration. Also, if U square is in quad precision, it requires a quad precision sparse solver, which from what I know does not exist, at least for parallel and scalable one. And it requires also the cast of the LU factors from precision UF to precision U square, which is a huge memory increase. That is why we wonder if we can relax this precision U square on the preconditioning. And it leads us to consider a new algorithm we call GMRIR5. So just to remind you, in GMRIR3, we are using a preconditioned GMRES by DLU factors to solve the correction equation. This GMRES has its precision depending on U, the working precision, and in GMRIR5, we make it independent of U, where UP, which is the precision at which we apply the preconditioning, may be less precise than U square, and UG, the precision of the other operations, may be less precise than U. We provide an error analysis of this new algorithm, and its convergence condition can be seen as a deal between LUIR3 and GMRIR3. It should be noted that the limiting accuracy does not change among these three algorithms, since it is solver independent. So here is few methods for making double precision solution. I display also the set of precision in place in different iterative refinement variants, as well as their condition on kappa A and the error accuracy they provide. The first one is DMOMS, which is the normal direct LU solving in double precision. Second and third one are LUIR and GMRIR, both performing the factorization in single precision. GMRIR is less restrictive on kappa A than LUIR. Also, we will consider two other methods, which I call the plus variant, and which are using quad precision for computing the residual. This allows to remove the dependence on kappa A on the error accuracy. I just have two comments on all these methods. For the GMS variant, since UP is different of UF, the LU factors need to be casted. All the iterative refinement variants presented here use single precision factorization to accelerate. We will consider half precision factorization a bit later in this talk. And to implement these variants, we use the multifrontal solver MEMS for factorization and LU solve operations. So let's make a performance study out of these variants. First, in terms of memory, what I display is the memory consumption of LUIR and GMRIR over 17 large suite sparse matrices, the whole normalized by elements. So we first see that LUIR consumes each time when it does converge 2 times less memory, which makes it a great variant to save memory. Also, interestingly, GMRIR5 gain over DMEMS, at best on this set 25%, despite that its factors are also in double. And this is possible because in multifrontal solver, the memory peak of the factorization is higher than the memory of the factors. Then GMRIR5 can gain on the difference between the memory peak and the memory of the factors. It may not be true for other kind of sparse solvers. If we consider using the plus variant for having a better error accuracy, we will add an overhead on the memory, which is on most of the matrices negligible. And when this is not negligible, it may be due to small matrices or small fill-in, which makes the copying quad of the matrix, the original matrix, for the computation of the residual, heavier in comparison to the factors in memory. So now, in time, what I display here is the same figure as for memory, but for time. And we can first see that, at best, LUIR is 1.7 times faster than DMOMS, which is pretty cool. Also, GMRIR is a bit slower than LUIR, because it asks more LU solves, but it does converge on all the matrices of the set, which makes it a more robust method. Both LUIR and GMRIR are gaining most of the time over DMOMS, but sometimes they are underperforming. And this may be due to small matrices or small filling. which makes the computation of the solve and the matrix vector product operations heavier in comparison to the factorization. Said in another way, it means that the refinement steps cannot be considered negligible in comparison to the factorization. And also it could be due to a high number of iterations required for convergence. If we consider now to use the plus variant to have a better accuracy, we will add an overhead as well on time, which is on most of the matrices reasonable. So in this previous experiment, we've been performing the factorization in single precision. Now we'll consider doing it in half precision. The bad news is a performance study with the factorization in half is a bit complicated because we don't have an easy access to half precision on CPUs right now, and direct sparse solving strategy using fully GPUs are not so straightforward. But to anticipate the availability of half on CPUs, we can still make a numerical study of GMRED IR5 with the factorization in half. This study focused on the robustness on kappa A, since this is the main interest of using GMRED IR5 over LU-IR3. We made it in Julia, which has a powerful modularity on the precisions and can simulate half and quad precision, which may be not hardware supported. Also, we made it on small dense matrices in comparison to the previous experiment, which was on large sparse ones. So we want to study the convergence robustness on kappa A of the following variants. We fixed the factorization in half, the working precision is fixed in double, and the computation of the residual in quad. The GMRES precision UG and the preconditioning precision UP are varying. So we wonder how to evaluate the robustness of these variants. Well, for UR in quad, the error accuracy should always converge to 10 minus 16. This is what says the theory. Then this is easy to determine if it converges well or not. And it makes it easy to compute the success rate of convergence, which seems to be a good measure to evaluate the robustness. So here what I display is the evolution of the success rate of convergence of LUIR over kappa A. Each success rate are computed from 100 randomly generated dense matrices, and we denote by the breaking point of the success rate, the point where the success rate begins to not be 100%, the point where it begins to decline to reach 0% of convergence. For example, for LUIR, this is located between 10.2 and 10.3. Of course, the more the breaking point of the success rate is high, the more the method is robust. So now if we compare LUIR with GMRED IR, here with UG in double precision and UP in quad, we see that we are far more robust because the breaking point is at something like 10.15. Also, if we choose UP in double precision, we see that interestingly, we kind of have the same behavior as for UP in quad precision. UP in single is less robust than UP in double and quad, but more robust than LUIR. It also means that UP has an influence on the robustness of the algorithm GMRED IR5. Now, if we let UG vary from double to single first, we see that UP in double and quad, which are the red and green curves, are getting less robust, which means also that UG has an influence on the robustness of the GMRED IR5 algorithm. If we choose UG in half precision, interestingly, we see that we are more robust still than LUIR, which means that even very low precision GMREs can have an interest. To conclude on my...
Okay, go ahead. Go ahead. We need to have some time for questions. Keep going.
Yeah, sure. I conclude quickly. So I presented just a new algorithm, GMRED IR5, which is practical for solving sparse system. And I presented a large experimental analysis with that, highlighting memory and time gains. Thank you for your attention.
Thank you. Well, there's quite a few questions in the YouTube chat, and I'll try to summarize them. There was a comment and question about the existence of quad precision sparse solvers that do exist that can be done or run on a Z series that has quad and hardware. Have you tried or looked into existence of quad precision solvers? I think
no,
these are...
we did not run quad solver directly. No.
Okay.
On the experiments, we just did the computation of the residual in quad.
This is referring to the quad solvers. I assume this is the LU factorization initially. It's being asked.
Yeah, this is located. here.
You had
Yeah.
a comment about the existence of about quad solvers, I think.
Right. Okay. I did not know.
Okay, and then other question: have you considered keeping the interim solution in additional precision?
Considering keeping, sorry, I did not
The
hear.
interim solution in higher precision.
The internal
Interim. Let's see. I think I'm not sure
interim.
if which. I was watching the chat out of sync with the what that referred to. I'm not sure. I think it's referring. Okay, I'm honestly not sure which. I thought that's referring to step 5, but that's what you're doing, isn't it? You have a different precision for step 5 there in the iterative solver.
Yeah. Um,
Maybe step 2. I'm not sure which question what that's referring to. For the forward back solves, perhaps. I'm not sure which solution is being referred to in the question. Let's see. Other comments about, here we go. I'm interested in solving linear systems with an SPD matrix. Could you modify the analysis to get a similar stability result when you replace LU factorization with Cholesky and GMRes with conjugate gradient?
I know that there is some things which has been done with considering Cholesky with iterative refinements. I think this is also. I think this is something which has also been considered by Carson and I. I'm not sure at all, but I think there is a recent paper on that. And for other kind of for other kind of solver at step 5, this is totally possible to use other kind of solver such as conjugate gradients. The interest of having MGS GEMRED here is that we have a strong theory behind that. We have a demonstration of the error analysis with MGS GEMRED.